In this video, we are going to look at how a resultant force works and motion under gravity. So we have mass of 3 kilograms, which is from rest, and a point that's 5 meters above the surface of a liquid. And it's in a container. There's no instantaneous change in the speed as it enters, and the length of the height is 4 meters. The downward acceleration is 5.5 meters per second. First of all, find the resistance to motion, and then we'll find some other details and sketch a velocity time graph. We have our SUVAT formula on screen as well. Generally that comes into play. Okay, let's have a look at the container. Always draw a little sketch beforehand. So there's no real detail on the container. It could be a box, it could be a tube. Doesn't really matter. Let's put in the details of what we're actually doing here. So we're dropping a particle into this container. We have a level of liquid at some point, and we have some measurements, some criteria there. So inside the liquid, it's a length of 4 meters, or depth really. And then we have, from the drop point, 5 meters. What else do we have? We have a mass of 3 kilograms as well. And our upward acceleration, we'll call it, is positive. So pick a direction for the motion, and whether it's positive or negative. So forces. We have what's called a resultant force. So going up would be your resultant, or our normal contact force. So we'll draw a little picture of this as well. And then your mass or weight, depending, is downward. And that's R for our contact force. So our equation of motion is F is equal to ma, and that's 3g minus r, and it's equal to mass times the acceleration, which is all given. So from here, plug in your details to find r. So 3g in this case would be 30. So 30 minus 16.5. Cancel on both sides, you get 13.5. So R, a resistance to the motion, is 13.5 newtons. Part 2, we're going to have to do some work before we get anywhere near a sketch. So we'll start with above, outside the liquid. Write out your SUVAT formula, whatever details you've been given. So the distance or displacement was 5. We started from 0, and the acceleration is 10. That's the motion of gravity. We've already chosen the upward motion as positive. So we have to choose one of these formulas, and often it's one of two. Really often it is the first one or the third one. And if it doesn't include time, it would be the last one that you see on the right hand side. And there we have 1 second was our time for that movement, that motion. Next, we see if we can find our velocity. So v equals u plus at. So we put in 10 for acceleration and 0, of course, for our initial velocity. So the velocity of that was 10 meters per second. That's outside above the liquid. Now, in the liquid, do the same thing again. So it's 4 meters. That wasn't 0 for initial when I put that in there. So remember that we're dealing with a stage here, so it's a stage upon another stage. So the velocity from the previous motion, the final velocity, is now our initial velocity continuing on. Keep in mind of that detail when you're dealing with multi-stage problems. Our acceleration was 5.5, and we'll continue on now. So can I find S? I think velocity. Yeah, that'll work. So 10 squared plus 2 times 5.5, and S is 4. So V squared is 144, and our V is, of course, the root of that is 12. And again, we're going to find time. We're doing a velocity time graph, so you want to find these details so we can sketch it. See how that motion plays out. V is equal to, V is equal to u plus at. We have our 4 details. You can actually use a few things here. And that should do it. 5.5. And our time. Divide both sides by 10, you'll get a small number here, 0.36. And this is cumulative now, so be careful here with the time. It should be clear, but just thinking about these things in terms of the physical world as well. That it took 1 second to go through from the outside in, and in the liquid it was a smaller 0.36 of a second. So our total time was 1.36. From there, we can do our sketch. Our velocity time graph. So V and T. So now I'm just going to plug in those 4 values in some way. Your sketch does not have to be perfectly accurate, but make it reasonably so. Just looking at the detail now of that. So it'll be 1 second. You could do from 1 to 2. You could do 1 to 1.5, 1.4 if you want, but just a sense of even spaces. And again, with the velocity, maybe you don't have to be so clear with that. If our values are from 10 to 12, you can just put in 10 and 12 a little bit above that. It would be fine. I'll put in a 5 as well, just for the sake of it. So our first values are 1 second, and the velocity is 10. Put a dot there, or an X. 1.4, just before your 1.5 at 12. Of course, these are straight lines. And that's pretty much it. That was a question on forces in one direction for Unit 2. And you can put in your 1.36 there as well. That might help.